Thank you everyone for coming to what promises to be a stimulating session. I'm Veller. I'll talk about the evolutionary significance of crossover patterning. There are two known forms of global crossover patterning. The first is crossover interference, discovered by L. Sturtevant more than a century ago, and the second we've recently reported is called crossover covariation. I'll talk about crossover covariation first, so this will require a detour into the world of crossover interference in any case. The observation that motivated this work is the fact that if you look at the number of crossovers per meiotic cell, you see this extremely wide spread. Okay, so these are data from human male spermatocytes, and you can see that the number of crossovers per spermatocyte shows us really great variance. And this is surprising if you think that crossing over is some evolutionarily important trait, to see this kind of variance. The first question you can ask is, does this variance come from intrinsic variance in the number of crossovers per chromosome? We can get at that question by using these data to pool all chromosomes 1, all chromosomes 2, and so on, and then constructing artificial nuclei, where for each nucleus we randomly draw a chromosome 1 from its pool, a chromosome 2 from its pool, and so on. So if we construct a lot of artificial nuclei that way, we find that they exhibit a much smaller spread in the number of crossovers per nucleus. And these observations, that the number of crossovers per meiotic cell shows this widespread, and that widespread cannot be explained by intrinsic variation in the number of crossovers per chromosome, seems to be conserved. So shown here for a few mammals, for a higher plant, for a fungus, and based on work by Kieran Samuk and Mohammed Noor presented yesterday morning, we expect to see the same pattern in Drosophila pseudoobscura as well. And we can actually be more precise about this. We can take the total variation in the number of crossovers per nucleus, and we can extract from it the contribution from intrinsic variation in the number of crossovers per chromosome. And what's left is a term due to covariation in the number of crossovers across chromosomes within individual nuclei. And so the fact that we've seen that this term in red is bigger than the blue term means that this total covariation term must be positive. That is, the number of crossovers per chromosome co-varies positively across the chromosomes within individual nuclei. Okay, we can actually see this directly in the data. So these are from human female oocytes, and you can see that in a given oocyte, if there are a lot of crossovers on chromosome 1, you tend to find that there are a lot of crossovers on chromosome 2. Or alternatively, if you look at the total number of crossovers on the odd-numbered chromosomes, you find that that's positively correlated with the number of crossovers on the even-numbered chromosomes. Okay, so how much of the total variance that we started with is being driven by this covariation effect? It turns out that crossover covariation accounts for the vast majority of the variance in total crossover number, as much as 83% in human female. That is, if crossover covariation were not a phenomenon, the total variation in the number of crossovers per human female meiosis would be 1/6 the value that it actually is. So it's really causing quite a lot of that. Okay, so we have this new phenomenon of crossover covariation. What is its mechanistic basis? Well, to understand the mechanistic basis of covariation, we need to understand something about the mechanistic basis of crossover interference. The crossover interference is this classical phenomenon where the formation of a crossover somewhere along a bivalent chromosome inhibits the formation of a nearby crossover. So that when another crossover forms on that chromosome, it needs to be a certain interference distance away from the first crossover. Now, at the stage of crossover designation in early meiotic prophase, the DNA is strung out into these long loops which are anchored along a linear common axis. And work in the meiosis field over the past 30 or so years, largely led by Nancy Kleckner, has shown that crossover interference actually propagates through the chromosome axis, so that the correct metric for the interference distance is actually physical length of the chromosome axis, right, measured in micrometers of axis length. And what that means is that if you take the same chromosome with the same number of base pairs and you string it out into shorter loops, therefore along a longer axis, you can fit more interference distances along that axis and therefore more crossovers. So in that way, the axis length of the chromosome determines the number of crossovers that you can fit along it. So returning to the mechanistic basis of crossover covariation, we know that chromosome axis lengths determine the number of crossovers in a positive relationship, And if we look at axis-linked data, we see actually that axis links also co-vary positively from chromosome to chromosome within the same nucleus. And those two facts are enough to explain why we see crossover covariation. So a final mechanistic question we can ask is, right, why do axis links co-vary? And a simple hypothesis that would account for axis-linked covariation is global modulation of chromatin loop lengths. Right? So if in this nucleus it has been determined by some factor that all of the loop lengths and all of the chromosomes are going to be long, then all of the axis links are short, and therefore there are few crossovers coordinately on all chromosomes. Whereas in this nucleus on the right, it's been determined that all of the loop lengths are very short, therefore all of the axis links are very long, therefore there are many crossovers on all chromosomes. I should say that the factors that determine chromatin loop lengths in early prophase are not well understood, but it's an active area of research in the molecular biology of meiosis. So returning to this question that I started with, why does evolution tolerate this very wide spread in the total number of crossovers per meiotic cell? Or now that we know that crossover covariation is driving most of that variance, why is the level of crossover covariation maintained by evolution? Okay, now the primary genetic effect of crossover covariation is to elevate the frequencies of gametes that have very many crossovers and the frequencies of gametes that have very few crossovers. And so we reason that this might be beneficial in a sporadically fluctuating environment. When the environment changes, new genetic combinations become favored. The fastest way to furnish these new genetic combinations is via recombination. It might be very useful then, after an environmental change, to have these elevated numbers of gametes with very many crossovers. Between environmental changes, you have a period of stasis, where the genetic combinations that are favored in the current environment are quickly produced, and you then really want to maintain those genetic combinations. So there it might be useful to be overproducing gametes with very few crossovers. Okay, so we wanted to test this logic in a formal population genetic model, and we constructed, I think, the simplest possible model for that purpose. So the organism is haploid. We're interested in covariation across chromosomes, so we need at least 2 chromosomes. We're interested in recombination along the chromosomes, so we need at least 2 loci on each chromosome, and we'll take that to be 2 alleles at each locus. Okay, so the life cycle of the organism is that these 2 haploid individuals mate to form a transient diploid stage in which a meiosis occurs. In that meiosis, there can be recombination on either chromosome. And we're going to include this covariation factor K. So when K is large, it is the case that if there's a crossover on the one chromosome, there's likely to be a crossover on the other chromosome. Well, similarly, if there's no crossover on the one chromosome, then covariation says there's probably no crossover on the other chromosome. Okay, so when K is large, you tend to overproduce gametes that have crossovers on both chromosomes or on neither chromosome, and you tend to underproduce gametes that have crossovers on only one chromosome. So the meiosis occurs to form 2 haploid products, which are the offspring, and the life cycle repeats. Okay, we include selectively relevant environmental fluctuations in this model in a very standard way. So in a given environment, we say that there's a favored haplotype on each chromosome. So in the current environment, on chromosome 1, it might be that big A, big B, and little a, little b are the favored haplotypes. That symmetry, incidentally, is a way of keeping allele frequencies constant while allowing haplotype frequencies to change. So we can really focus on just the linkage relations between the alleles. That is the effect of recombination itself. Each generation with probability 1 over t, the environment changes, so that the average length of time between environmental changes is t generations. When the environment changes, the favored haplotype changes on both chromosomes with probability p, or on just one chromosome with probability 1 minus p. Okay, so when p is large, an environmental change selects for recombination on both chromosomes, therefore favoring crossover covariation, which overproduces gametes with crossovers on both chromosomes. Whereas when p is small, environmental changes typically favor haplotype changes on only one chromosome, and that's bad for crossover covariation because it underproduces gametes with only one crossover on just the one chromosome. Okay, so when p is large, that's good for crossover covariation, and when p is small, environmental changes themselves are bad for crossover covariation. Okay, and the general strategy to see if there's a selective advantage to crossover covariation is to take 2 populations, one with covariation, one without, and to compare their growth rates in this fluctuating environment. That is their geometric mean fitness. And so when we do this, these are the sorts of results that we see in the simulations. Okay, on the y-axis is the selective advantage, the growth rate advantage of crossover covariation. On the x-axis is p, the probability that an environmental change selects for recombination on both chromosomes. Okay, and there are a few things to see from these results. The first is that crossover covariation generally shows a selective advantage relative to no covariation. Okay, that selective advantage is monotonic in the degree of crossover covariation, and consistent with our intuition, when p increases, the advantage to crossover covariation increases, because then environmental changes themselves are favoring crossover covariation more. Nonetheless, when you look when p equals 0, and we know that environmental changes themselves disfavor crossover covariation, nonetheless crossover covariation shows a selective advantage. So where could that be coming from? Well, we reason that it must be coming from, because the environmental changes themselves are bad for covariation, it must be coming from the stasis periods in between environmental changes, when crossover covariation can be favored, because it overproduces gametes with few crossovers, with none in this model. Okay, and by that logic, it should be the case that as we increase the period of stasis between environmental changes, the advantage to crossover covariation increases in the case that p equals 0, and that's precisely what we see here. Okay, so in conclusion, I've shown you a new form of global crossover patterning, that the number of crossovers co-varies positively across chromosomes within individual meiotic nuclei. This crossover covariation appears to be conserved across eukaryotes. I've argued that crossover covariation is caused by an analogous covariation of axis lengths in early meiotic prophase, and I've speculated that this axis-linked covariation is driven by global modulation of chromatin loop length at that phase of meiosis. And finally, I've argued that crossover covariation, and indeed the maintenance of variation in the number of crossovers per cell in general, might be beneficial in a sporadically fluctuating environment, which is faced by most species. So with that, I'd like to thank my collaborators on the project, Nancy Kleckner, Martin Novak, Chunxin Wang, and Liang Zhang, and my department for funding. Thank you. Mark?
Have you tried seeing how this evolves with a modifier rather than comparing two populations?
It's in the works. It's in the works. This was a sort of quicker version. We expect the results to be the same, but we'd like to confirm it with formal modifier analysis.
No, it's not so much a question of a comment. I wonder how this ties in perhaps the heritability of the combination rate. As if the combination rate has done through successive generations inheritable.
Yes.
And how that ties in with
So I should say that the extreme variation that's seen is in fact within individual variations. We see already the same amount of variance that you see within the species overall is actually seen within the myocytes produced by the same individual. So I'd love to know how heritable the variance of crossover number is. The data in almost all cases is not there yet to test that yet.
So you've shown with the model that there's a conceivable advantage of this crossover covariation. How would you test against an alternative hypothesis that it's not an adaptation? It's just like the organism can't do any better than this level of covariation.
Yeah. So it would be nice. It would be nice, for example, to have, if we know that sort of if we look at variation and covariation across species, it would be nice to have maybe a comparative test.